I want to start with the definition of the Brownian motion. You are probably all familiar with this definition, but let's go over this again. A stochastic process, and a stochastic process is a collection of random variables, as you know. In this case, the collection of random variables is indexed by the real variable t, and we say, and t is defined on a finite interval from 0 to capital T. We say this is a standard Brownian motion on 0t if W0 is identically 0 to the stochastic process has independent increments, which means if you take any time points on the t-axis, t1, t2, tn, and then if you look at the differences in your stochastic process, the increments, wt2 minus wt1, t3 minus t2, etc. These increments, these differences will be or are independent random variables. And finally, for s less than t, if you look at wt minus ws, that difference is going to be a normal random variable with zero mean and variance that is equal to the time difference, t minus s. Now, a generalization of this definition is the Brownian motion with drift mu and diffusion coefficient sigma squared. And in the generalization, you replace the third condition by this condition. What's blue, and now mean of the normal distribution is no longer 0. It's proportional to the time difference, some constant mu times the time difference, and the variance is going to be sigma squared times t minus s. So mu and sigma are the parameters, okay, that are given. Now, the history of Brownian motion goes back to Brown, who gave his name to the stochastic process. Robert Brown was a botanist, and in 1827 he realized that pollen grains in a jar of liquid kept moving around, bouncing around, and he couldn't understand why these dead grains are moving. What movement? He didn't have an explanation. Louis Bachelier independently introduced Brownian motion and used it to model stock prices, actually, as early as 1900s. And after 5 years later, Albert Einstein gave a mathematical analysis of Brownian motion, and he showed that the movement Brown observed can be explained by assuming that the pollen was continually being subjected by the molecules of the surrounding medium. And finally, in 1918, Wiener gave a rigorous analysis definition, the brief history of Brownian motion. Let's talk about the stock price model he used in his PhD dissertation. Let ST be the stock price at time t, and the model assumes that the difference in the stock price, so think about T0, T0 as today, and T as some future time, maybe 2 days from today. So the difference in the stock price between that future day and today is going to be a normal random variable, with a mean that's proportional to the time difference, a variance that's proportional to the time difference. And also we assume that this increment, that the jump in the stock price is going to be independent of all prices up to time t0, like the Markovian property. Now, there are two problems with this model. One of them is ST can be negative. right? This normal distribution can take negative values. So that could mean that ST could be negative. We don't want that stock price. We don't want stock price to be negative. And more importantly, according to this model, the following two events have the same probability. So the first event here is that the stock price increases from $10 to $20 in 1 day, % increase. And the second event here is that the stock price increases from $100 to $110 in 1 day, which is merely a 10% increase. However, in each case, the net increase in the stock price is $10. So in each case, ST minus ST0 is going to be $10, but then it's going to be modeled by the same normal random variable. So the probabilities are going to be exactly equal to each other, which is not realistic because a 100% increase in the stock price shouldn't have the same probability as a 10% increase, which tells us that we shouldn't be looking at absolute differences. We should look at relative differences in modeling stock prices. And that's what Samuelson did. Samuelson was an economist, and he read about Bachelier's dissertation. He actually got it translated to English. And then he, instead of differences, he looked at ratios in the stock price. And then also he took the logarithm of that ratio and modeled that using a normal distribution. This way, even if the logarithm is negative, that means the ratio is going to be always positive. And that's when we talk about Black-Scholes model or Black-Scholes-Merton model, this is the model that we are talking about. And in the literature, we often see this model written using a stochastic differential equation, an SDE. I will talk a little more about SDEs, but not a lot. And in this stochastic differential equation, you see the change in the stock price divided by ST. That's given by mu dt plus sigma dWt, where this is your Brownian motion. Now, financial derivatives are functions on the line, typically a stock price. Functions, or well, here's a more financial definition. They are claims that promise payment in the future depending on the behavior of the underlying asset. For example, a European call option is a financial contract that gives you the right to buy an underlying asset for a fixed price K at some future time, capital T. And the payoff function is given by this expression. That's the maximum of the final stock price minus that fixed price, the strike price K, comma 0. So if this difference is greater than or equal to 0, that's the payoff you have. If this difference is negative, which means your stock price is less than K, then the option does not give you a payoff. You don't lose any money. The only money that you lose is the initial investment you made to purchase the option. And we use this notation for shorthand, ST minus K plus. Okay. A European put option is similar to a call option. The only difference is in the call option, we are purchasing the right to buy. Here we are purchasing the right to sell an underlying asset for a fixed price K at some future time, capital T. And now, instead of the maximum ST minus K, now we're looking at the maximum of K minus ST and 0. So that's reversed. There are many more financial derivatives, many more options, different payoff functions, give you different options. And here you see a bunch of them. And also sometimes the payoff function depends only on the final stock price, like in the digital option or the European options. But sometimes the payoff function depends on the entire path of the stock price, like in this ratchet option or arithmetic option, arithmetic Asian options. Another important distinction in the world of option is the European versus American options. When you have a European type option, you can only exercise your right to buy or to sell the underlying at the expiry. If you have an American option, you can exercise your right anytime, between now and the expiry. So that makes American options a little more complicated to analyze. I want to give an intuitive introduction to risk-neutral pricing, a very intuitive introduction to risk-neutral pricing. Many of you may have seen this concept before, treated in a more rigorous way. So I want to start with this question: present value of $10 promised at future time t. And so if I tell you that I'm going to give you dollars years from now, well, the inflation, the interest rate, that money is not going to be the same as $10 I have now. So we have the discounting rates, right? So if R is the risk-free interest rate, or the rate that you get in a savings account, then you need to discount $10 by multiplying it by e to the power negative RT to find its present value. Right? Because if you invested this much today, 10 years, it is going to grow to $10. So that's how you find the present value of a cash amount. Now I'm going to make the problem a little more complicated, and I'm going to say, this time I don't have cash, but I have a financial derivative. Okay, so like what we talked about on the previous pages, a call option or a put option or something like that. And I want to know the present fair price, and I'll tell you what I mean by a fair price in a minute, of a financial derivative at some future time capital T. And this financial derivative have this payoff function f. Now, this second question is a lot more complicated than the first question. Now, for one difference is that the first question, this $10, that's cash, that's a fixed amount. But here, the payoff f of s capital T is not a fixed amount. It is a random variable, because s is a random variable, and if you're using the Samuelson's model that we talked about before, the ST would be subject to this differential equation, to the stochastic differential equation. So it's not. So what I'm trying to emphasize is that it's not fixed. It is a random variable. So this is now a more difficult question. And then not quite sure how we would discount the amount to the present. When we have a fixed value, we can discount it using the interest rate, but we're not sure how to do it in this situation. In the literature, before, like Scholes wrote that seminal paper, for which Scholes and Merton got the Nobel Prize in economics, people were trying to find formulas like this for the price of a financial derivative, fair price of a financial derivative. So here that this gamma 2, okay, so first we want to find the average payoff for this derivative at that future time capital T. And average payoff means we need to find the expected value of this random variable. To find the expected value of this random variable, we need to figure out how S grows. That's the appreciation rate for the stock price. And then so maybe let gamma 2 be the appreciation rate, thus how much it grows. And once you find the average payoff for your derivative, you need to discount it back. And it's not obvious what discounting rate you should be using. And in general, let's say gamma 1 constant is the appropriate discount term for the derivative. And that discount term for the derivative is going to be the roughly the growth term, how much the derivative is growing at rate gamma 1, so that when you discount it back, you find its present value. So once again, in the literature, people wrote a lot of papers trying to find these rates, gamma 1, gamma 2, what they should be. It wasn't until the papers of Black, Scholes, and Merton, Cox, and Ross that people realized that these constants, gamma 1, gamma 2, they both must be equal to R, the risk-free interest rate. They must be equal to R in the following sense. If they are not R, then we have arbitrage. We can buy and sell this financial derivative and also borrow money, construct a portfolio, and immediate profit with no risk. So this is known as risk-neutral pricing. Now, pricing options using Monte Carlo simulation is pretty straightforward. Once we decide on our risk-neutral probability measure, risk-neutral dynamics, all we need to do is simulate a price path. Okay, so ST1, ST2, S capital T. So this is going to be a stock price path from today, which is called T1 today, higher. And then for each path, I can compute the payoff. So F is the payoff for the derivative. And then I will generate many such paths, capital N of those. And I'll just take the average of these payoffs. Once I compute the average payoff, I can find its present value by multiplying to the power of negative y. And that would be the Monte Carlo estimate of the price of the option. Now, how do I generate the price path? The Black-Scholes-Merton model, that's BSM, also called the geometric Brownian motion model, or the Lognormal model, is given by this STE. In the risk-neutral dynamics, you replace mu by R, the risk-free interest rate. And the solution of this STE is given by this expression. So if you want to simulate, ST, you need to simulate WT. And in general, if you want to simulate a path, ST1 to STN, you need to figure out how to generate this Brownian motion path, WT1 through WTN. So let's talk about how to simulate a Brownian motion. So what exactly does that mean, simulating a Brownian motion? Well, first of all, you have to start with discretizing time. So let's say today is 0, that's T0, and then T1 through Tn, these are my time points. And I want to simulate the value of my Brownian motion at those time points, Wt1 through Wtn. Now, from the definition of the Brownian motion, the third part of the definition, we know that these increments, WT1 minus WT0, WT2 minus WT1, these increments have distribution, normal distribution with mean 0 and variance that's equal to the time difference. And they're also independent. So this is the fact we need to be able to simulate these random variables. How? Well, we're going to start with first generating n independent standard normals, Z1 through Zn. And then we're going to set WT1 equal to this radical multiplied by Z1. So that makes WT1 a normal random variable, mean, because Z1 has 0 mean, and variance that's equal to the square of this quantity, which is T1 minus T0, and that's exactly what we have here. And then I'm going to set WT2 minus WT1 equal to the radical of the time difference multiplied by Z2, and this equation makes WT2 minus WT1, this increment, a normal distribution with 0 mean and variance T2 minus T1. Okay, so once again, this definition is satisfied. And of course, since you know WT1 from the first step, you can get WT2 by adding WT1 to both sides, and then you continue like this, and that's how you generate your process. Now, okay, so we said on the previous page I said we need to simulate normal random variables, but how do we do that? Something we didn't talk about before. That's the first question. How do we generate numbers from the normal distribution? And can we do it using Monte Carlo and quasi-Monte Carlo? I learned about quasi-Monte Carlo methods in the first 2 lectures. And maybe before we talk about these first 2 questions, we should talk about the third question. Why would we want to even think about using quasi-Monte Carlo? Well, here's a picture. In this picture, we are pricing a digital option, and we are plotting the absolute error. We can find the exact price of a digital option analytically. So we plot the absolute error of our estimate against the sample size, and the sample size is going up to 10 to the power 8. And I'm using 3 methods to price this option. The curve at the top, a pseudo-random number generator. This calculation is actually done on a distributed machine, and we are using a parallel random number generator library. It's called Spring. So SPRNG is that parallel random number generator. And these 2 plots that are they are very close to each other are 2 scrambled versions of the 4 sequence, scrambled 4 sequence and linear scrambled 4 sequence. And as you can see, this randomized quasi-Monte Carlo approach is much better than the Monte Carlo simulation in terms of the convergence rate. Okay, and in practice, many people have observed that when you use quasi-Monte Carlo in pricing options, you typically get convergence rates very close to 1 over n, no matter what the dimension, the nominal dimension is. And we explained that by saying that in most financial option pricing, the effective dimension of the problem is close to 1. So for these reasons, pricing options via QMC is pretty popular among financial engineers. Okay. Now, before I continue, I want to take a break and then talk about this definition, which is a very simple definition that was mentioned by Sobol in a book he wrote, I believe. It's a simple definition, but very useful when you are trying to re-implement a Monte Carlo algorithm using quasi-Monte Carlo sequences. So this is the definition of the constructive dimension of a Monte Carlo algorithm. So let's say that you have a Monte Carlo algorithm, and I'm going to denote that by this function f, a black box function f. You input n random numbers, not n, s pseudo-random numbers. And when you input s pseudo-random numbers, this Monte Carlo algorithm gives you an output. Okay. Then we say the Monte Carlo algorithm has constructive dimension s, little s. And you need s-independent pseudo-random numbers. In our input, we say s is the constructive dimension. So if you want to rewrite this algorithm using low discrepancy sequences, then you will need to use a conventional low discrepancy sequence. In the examples I'm going to give you today, unfortunately, all the time my effective dimension is 1. I had to remove some higher effective dimension, constructive dimension, excuse me, because my lecture was too long. But, better keep this definition in mind if you will work with low discrepancy sequences in the future. So now we will learn about how to generate pseudo-random numbers from non-uniform distributions, because in particular we're interested in simulating normal random variables. Now, a standard method is the inverse transformation method, and in the context of pseudo-random numbers, I want to talk about this method now. So the question is, how can we generate IID random variables, pseudo-random numbers from a non-uniform distribution F? And so the inverse transformation method is described in the form of a theorem here. Let's read this. 1 through un are IID random variables from the uniform distribution on 0, 1. And if f is the CDF of some random variable, and if you apply the inverse of that CDF to your UI and let them be xi, then the xi are going to be IID random variables from the distribution f. And the proof of this theorem is really just a single line. I can just read this quickly. But it's not the proof that's important. The theorem is extremely useful. And it tells us that all we need to do is apply the inverse CDF to our pseudo-random numbers to generate random numbers from the target distribution. What about in the context of low discrepancy sequences? In lectures 1 and 2, when we talked about the low discrepancy sequence, we always considered the uniform measure, the Lebesgue measure on 0, 1, or the S-dimensional unit cube. What does it mean to generate a sequence from a non-uniform measure? Well, here's the definition of a UD mod 1 sequence that we talked about earlier in lectures 1 and 2. So we need to generalize this definition to a non-uniform measure. And that's done simply by replacing b minus a by mu of the interval AB, where mu is any measure. If mu is the Lebesgue measure, then you get b minus a. And in general, it's, you have a non-uniform measure. And corresponding to that definition, we can define a star discrepancy using a non-uniform measure. And if you compare this star discrepancy with the one that we talked about in lecture 2, the only difference is that before we had the Lebesgue measure, the uniform measure here. Now it's just some mu. And this theorem, partially proved by Chelsea in 1976, and then correctly proved by Eisleitner and Dick in 2010, gives a Cox-Malawka type inequality, where, as you see, the integral is now the integral has a non-uniform measure, okay? And the integration error is bounded by the variation of the function multiplied by the star discrepancy in that non-uniform measure. So these are the basics that we need to know. Okay, so let's talk about some examples. If I have a discrete distribution, how would I simulate from that using the inverse transformation? So have a look at this discrete distribution. X is my random variable. The probability that X takes the value Xi is given by Pi. And the I can be countable or I can be finite. The can take finitely many values or countably many values. So to sample from this discrete random variable X, okay, you start with generating a pseudo-random number U from the uniform distribution on 0, 1, and then you simply try to find the subinterval that U falls into. Okay, so what am I talking about? I am breaking 0, 1 into subintervals. The first one is going to be from 0 to P1, and if U falls into that subinterval, output is going to be X1. The second subinterval will go from P1 to P1 plus P2, and if U falls in that interval, then you will be simulating, you will be outputting X2, and so forth. And you can show that this definition or this description is really the inverse of the CDF of your distribution function. And if your distribution function is not invertible, then it's the generalized inverse function. Here's a simple example, a very simple example of a discrete distribution. Here I have a uniform distribution, a discrete uniform distribution on the integers 1 through n. That means the probability that X takes the value I is 1 over n, that's fixed value. So how do I simulate that? If I just follow the algorithm or the method that we talked about 2 pages ago, I generate a pseudo-random number U between 0 and 1. And if U falls into this subinterval, then X is equal to I. Okay, this just follows from what we talked about. This is the sum of the PIs, the first I minus one of them, and this is the sum of the probabilities, the first I of them. And if you do this simple inequalities in the simple algebra, you come up with this simple formula. X is equal to the floor of n times U plus 1. So you simply generate a uniform random number U and compute this expression to get a pseudo-random number integers. So here's an example. How would we do that using a low discrepancy sequence? How would we simulate from the uniform distribution using a low discrepancy sequence? On the previous page, we learned that to simulate, we need to do this calculation, NU plus 1. So think about the algorithm. The algorithm takes U as the input, and then it outputs floor NU plus 1. So then the constructive dimension of this algorithm is simply 1, right? It just requires one pseudo-random number. So since the constructive dimension is 1, I am going to use a one-dimensional quasi-Monte Carlo sequence, and here this is the one-dimensional van der Korpel sequence. And I'll take the first 1,000 numbers, and then I'm going to input, each number in place of U. So it's floor 50 times. Here n is 50. So you do this. And in the first picture here, the first histogram, I do this using pseudo-random numbers. And the second histogram, I am using my van der Korpel numbers as I explained. If you compare these two pictures, you're going to realize how the low discrepancy sequence, the van der Korpel sequence, gives you a much closer relative frequency histogram to the flat, to the constant density function of the uniform random variable. And in pseudo-random numbers, you see a lot more variations. And here's another example. This time I'm looking at a continuous distribution. It's an exponential distribution. And here's a definition of an exponential distribution. And here's the CDF. And I need to find the, I need to find the inverse of this function, but that is an easy thing to do. That's just algebra. And here's the inverse. Now, so what I'm going to do next is I will compute f inverse u. So I'll replace x by u, where u is my uniform 0, 1 random variable, or my pseudorandom number. But then 1 minus u, if u is a uniform random variable on 0, 1, 1 minus u is also a uniform random number, a uniform random variable on 0, 1. So 1 minus u and u have the same distribution. So we can actually replace here, replace 1 minus x simply by x when we do the substitution x equals u. The simple algorithm: generate your uniform random number, and then set x equals negative log u divided by lambda. And here's a picture. On the left, I generate 1,000 pseudo-random numbers, and then transform them to numbers from the exponential distribution. And here I do it using my low-discrepancy sequence. In this example, the constructive dimension is also 1. So I'm using a van der Kolk sequence in base 2. It's a little more difficult to distinguish these two pictures, these two histograms. For one thing, the x-axis are actually, axes have different scales. If you look at the pseudo-random plot, you're going to see 20 here on the x-axis, and then maybe it goes up to, what is that, maybe 25, or maybe less than that. But the QMC sequence doesn't go as far on the x-axis. So this tells us that the pseudo-random simulation probably have more outliers than the low discrepancy sequence. Okay, and finally, the normal distribution. Here's the density of my normal distribution. And here are some facts about normal distribution that you probably all know from your probability courses. And if you want to use the inverse distribution method to sample from the normal distribution, you need to invert the CDF. But as you know, the CDF of the normal distribution cannot be expressed as an elementary function. So you have to use a numerical method to invert this integral. And one popular numerical method in the literature is, for example, the Beasley-Springer-Morrow algorithm. There are other methods to sample from normal distribution, but I won't be talking about them. Finally, this is going to be our last distribution, log-normal distribution. This is important because log-normal distributions are what we come across in the geometric Brownian motion model. The random variable y is said to have log-normal distribution with parameters mu and sigma squared, and it's written in this way. If y can be written as e to the power x, where x is a normal distribution with those parameters. So the mu and the sigma squared are the mean and the variance of that hidden normal distribution. And you can compute the expected value and the variance of this log-normal distribution quite easily using the moment generating function of normal distribution. You can also obtain expressions for the distribution function of the log-normal distribution. It's density function after you differentiate the distribution function. You can find that this remark tells us that the median of y is e to the power mu. Therefore, the mean of y is larger than its mean, implying positive skewness. And how do we simulate a log-normal random variable? Well, that's really not very difficult, because a log-normal random variable y is nothing but e to the power x, where x is a normal random variable, and we know how to simulate x. So all you do is simulate from x and then compute e to the power x. Now let's start talking about stochastic processes. And this was the Brownian motion definition that we talked about before. And some about the Brownian motion, and I'm probably sure you have seen these in your probability classes before. And then this was the definition of the Brownian motion with drift mu and diffusion coefficient sigma squared. And to simulate the Brownian motion, there are a number of methods. First, I should say that. The simplest one is the random walk construction, which directly follows from the definition, and we actually talked about this earlier. And then another popular construction is the Brownian bridge construction, but we're not going to talk about that in this lecture. So again, we talked about this earlier. If I want to simulate the Brownian motion, I need to simulate first my normal random variables, z1, z2, zn, from the independent normal numbers from the standard normal distribution. You just set WT1 and the differences as given by these equations. If your Brownian motion is not standard Brownian motion, but it has drift mu and diffusion sigma squared, then these equations are modified by adding the appropriate drift term, and also by multiplying the radical terms by sigma. Now so we talked about Brownian motion. Now let's define what a geometric Brownian motion is. ST is a geometric Brownian motion if log ST is a Brownian motion with initial value log S0, or equivalently, if ST can be written as a constant times e to the power xt, where xt is a Brownian motion. Now, if xt is a Brownian motion with these parameters, then it satisfies the stochastic differential equation given by this equation. Here with Ito's formula, and I mentioned Ito's formula in this lemma here. Ito's lemma allows you to find the STE that is satisfied by a function of xt. And in this case, I'm going to find the STE satisfied by ST, okay? And ST is a constant multiplied by e to the power xt, so that's the function I'll be using for capital F. I'll skip the details, it's calculus mostly, but if you go through Ito's formula, then you'll find that the stochastic differential equation satisfied by ST is given by this expression. Now notice that here we have mu plus sigma squared over 2. All right, and I'm gonna just say something about that next. We had mu plus sigma squared over 2 in that expression, but in the literature, geometric Brownian motions are typically specified through an STE, where that first term is not mu plus sigma squared over 2, mu. So if you start the stochastic process for ST with a mu as the drift term, then you can go back and find the stochastic differential equation for xt using Ito's formula again, but this time you will be using not e to the power x, but log x as the function capital F in Ito's formula. Then you will find that the stochastic process for xt is has mu minus sigma squared over 2 as the drift term. So what I'm trying to explain here is that depending on where you start, going from st to xt or xt to st using Ito's formula, you will either be adding sigma squared over 2 or subtracting sigma squared over 2 from the drift term. And so here is now our the standard Lognormal model that we use for our stock price. ST is equal to 0 multiplied by this exponential term. This neutral pricing, mu will be replaced by R. And here's the final definition for the geometric Brownian motion. And to simulate the geometric Brownian motion, you discretize time. And here how you can go from STI to STI plus 1. This is the same equation that we were looking at like 2 pages ago. The only difference was at ST0 or S0, the starting stock price. Here I had the final stock price. Okay? So by simply modifying your beginning time and then ending time, you can simulate your stochastic process at each time. If we were simulating a Brownian motion, we would be using this blue equation, and then take e to the if you just take the exponential of the blue equation, you don't get the red equation. That's the interesting thing about Ito's formula, Ito's calculus, right? This term mu is replaced by mu minus sigma squared over 2. Now, if you wanted to use quasi-Monte Carlo to simulate the geometric Brownian motion, then we will have to be careful with the way we simulate our standard normal random variables. Now, here I'm using 2 indices. Earlier, I just had a zi. Now I have zij. So what you do is, if the number of time steps is little n, that tells you that the constructive dimension of the algorithm is little n, which means you need to use an n-dimensional low discrepancy sequence. So let's denote by phi j the jth element of an n-dimensional quasi-Monte Carlo sequence. So here's how phi j is written. So what we want to do is if we want to simulate the jth stock price path, the jth path, you need to have these numbers, z1j, z2j, z3j, until znj. And those numbers will be obtained from the jth vector, the jth element of the sequence. And how are they obtained? By applying a transformation method to it. So let's say capital M is the transformation method, that when you apply capital M to a uniform random number or a number from the uniform distribution, you obtain a number from the normal distribution. Then you set zij equal to m of phi sub I j. Okay, and so this inner for loop, as I goes from 1 to little n, this phi ij will be going through each component of the jth vector, and that entire vector then gives rise to the jth stock price path through this equation. And here's that dependence. And then subsequent vectors of your quasi-Monte Carlo sequence give you subsequent price paths. And once you generate these paths, then you can compute the price of your option on them, and then you can average, and then that's so as a final example, I wanted to show you how to price Asian arithmetic call options. An Asian arithmetic call option has this payoff, where S bar is just the average arithmetic average of the stock prices. So on the previous page, we were looking at this formula, not this code, this for loop we talked about in the previous page. How we generate the stock price paths. Now, for each stock price path, I am computing the average stock price. And then I am computing the value of the option for that ith path, which is S bar minus K plus. And then at the end of this loop, I compute the average of all these prices, all these call option prices. I average them, and then I discount. I bring them to the present time. So this Cn hat is now the price of your Asian arithmetic call option, estimated by Monte Carlo or quasi-Monte Carlo simulation. That is the end of my talk. Thanks for listening, and I hope you enjoyed these lectures. Bye.